So the previous question was discussed by Shailendra. Now we'll move to our next question. So this is the given question which we have also seen in the PDF. So what this question says is estimate the self diffusivity of liquid mercury at three different temperatures using following data at pressure equals to 1 atm. So what do we have to do in this question? We have to estimate self diffusivity at different temperatures. So what are all those different temperatures? So this is given in this data. Okay, so we can see these are the three different temperatures. First one is 275.7 Kelvin, 289.6, 364.2, so on. Similarly, for corresponding three different temperatures, we have also been given the viscosity in terms of centipoise for all those. So they are namely 1.68, 1.56, 1.27. And the third parameter which we have been given is it is specific volume. Okay, centimeter cube per gram. So these are the values for different temperatures. Okay, so now we're going to estimate self diffusivity. So this is the formula for self diffusivity. I hope you all are able to see it. I hope it is visible. So this is diffusivity of AA. So this is self diffusivity into viscosity of A upon kT equals to 1 upon 2 pi into Na upon this specific volume to the power 1 by 3. So this is the formula, and what we have to calculate diffusivity based on this data given. So now we'll move ahead. Yes, so after the manipulation we have this self diffusivity in this simplified formula. So here it is kT upon 2 pi mu A upon Na upon specific volume to the power 1 by 3. So K is Boltzmann constant. Okay, T is temperature, mu is viscosity, and A is what? Avogadro's number, and VA bar is specific volume. So we all have data. Now we'll simply substitute and get the value. So these are the values for the mentioned variables constant here. So K is 1.38 into 10 to the power minus 16 into temperature. So now we are estimating at this very first temperature 275.7 upon 2 pi mu A. So this is 1.68 into Na. What is it? Avogadro's number. We already know what is the value for Avogadro number. It is 6.022 into 10 to the power 23 upon this value I'm talking about. Okay, so specific volume. So this is 0.0736. We have taken this value here to the power 1 by 3. After putting this in the calculator, we will get the self diffusivity with respect to temperature 1, that is 275.7 Kelvin, is this in terms of centimeter square per second. So this value comes out to be 7.26 into 10 to the power minus 7. Okay, and this is just a minute. So after calculating the diffusivity, self diffusivity at temperature, this 275 will move to this and later this. So for 289.6 Kelvin, we have the same formula, this one, and we have simply substituted by changing the temperature, self diffusivity, and viscosity. So in this case we have put down all these values so that we can calculate self diffusivity in the case of second this thing. Okay, so the value come out to be 8.21 into 10 to the power minus 7 centimeter square per second. Now we'll look what is the self diffusivity for 364.2 Kelvin. Okay, so yeah, so as mentioned, we are calculating the self diffusivity at temperature 3, that is 364.2. Similarly, we have taken the different values of viscosity and specific volume as well. Okay, and after substituting all these values in this formula for self diffusivity, we get the value as 1126 into 10 to the power minus 6 centimeter square per second. Okay, so we are also done with this question, and now we'll move to another question. Okay, so now we are moving to our next question. So the next question is this. So we have to estimate what we have to simply estimate diffusivity for dilute solution. Previously we were solving for gases, and now we'll look into the liquid as well. Okay, so we are calculating diffusivity for dilute solution of TNT. TNT is 2, 4, 6 trinitrotoluene. I hope you all are already aware of this. This is very popular compound in benzene at 15 degrees Celsius. So we have to simply estimate DAB, okay, for a dilute solution. So first we'll look at the solution, what we have to do. So here it is mentioned that we have to use the equation of Wilk and Chang, taking TNT as compound A. So we have taken TNT as compound A and benzene as component B. Okay, and the viscosity of pure benzene is what? 0.705. This is what, let me just a minute. Okay, so this is, after this we have been given the molar volume for TNT, which comes out to be 140 centimeter cube per gram mole. Okay, this data we are already given with, and this is 5b equals to 1 for benzene, and molecular mass for benzene is 17.811. Okay, so now in order to calculate diffusivity in the mixture for liquids, we have this formula, which is 7.4 into 10 to the power minus 8 into root of 5b into mb into t square upon mu into molar volume to the power 0.6. So they have mentioned temperature at 15 degrees Celsius. So we have to convert this into what? Kelvin. So we have done, this is 288 Kelvin. Okay, now we have all this data. Simply we have to substitute the values and get the value of DAB. Okay, so after substituting the values, we have already substituted here, and we'll get the value of diffusivity at 2.18 into 10 to the power minus 4 centimeter square per second. Okay, now we'll move to another question. Okay, so now we'll move to our another question. So in this question they have told us to estimate diffusivity for the system CO2. Previously we have calculated the diffusivity for CH4 and C2H6, that is methane ethane system, and in this case we are calculating for carbon monoxide and carbon dioxide at this mentioned pressure and temperature. Okay, so now we look at the solution. Okay, so from table, which I have also shown you for the previous question, similarly we have taken the values from that table. Okay, I'll show you for this question as well, so that you all can have understanding, proper understanding. Okay, so from table, first CO, we have declared this as component A and CO2 as B. Okay, molecular mass is 28.01, 44.01. Sigma, which is collision diameter in terms of angstrom, is 3.590, 3.996. Epsilon by K is 110 and 190. Okay, so I'll explain you how we have got this data and from where we have got this. Okay, and moving further, now we'll have to calculate the sigma AB for the mixture. Okay, so this is the average mean of sigma A plus sigma B by 2. So sigma A is what? This is simply collision diameter for A and B. So we have already these values. So we'll have substitute this and we'll get the sigma A B value as 3.793 angstrom. Okay, now we have already epsilon by k, but we have for individual component. But what we have to do? We have to calculate for uh, system for CO2. So this epsilon A by AB by K combined form. So this is under root of epsilon by K of A into epsilon by K into B. So these are these values. Simply we have multiplied it, under root we have taken, and we got the value as 144.6. But we don't want epsilon AB by K. What we want KT by epsilon AB, so that we can calculate what? Collision diameter. Okay, so we have calculated this. After putting this value, we got this 2.048. Okay, and from the collision like from the table, we have got collision integral as 1.067. Okay, from the table. And now I'll explain you how I got this data and how we have calculated this using that table. Okay, so just a minute. So yes, let me explain you how we have gathered the data. So this is simple polyatomic gases. Okay, so CO2 was our system. So corresponding to these, we have molecular weight sigma and epsilon by k. Okay, so CO 28.01, 3.590, 110. For CO2 44.01, this is molecular weight sigma, which is collision diameter 3.996, 190 for epsilon by k. You can also verify it from here as well. Okay, and now for collision integral, these are the values. Like here you all can see this was the estimated kT by epsilon AB 2.048, and corresponding to this we have to calculate collision integral. So now I'll let you know how we have done this using these table, so you all can have a look here. So this value kT by epsilon AB is 2.048. This is not exact, but here it is exact. So we have to interpolate these value, like from in between 2 and 2.1. Okay, so we'll have to interpolate, and after interpolating we'll get the value corresponding to 2.048 between these two value, 2 in between this value. So here we can have look 1.067 is between both of these value, isn't it? Of course it is. So this is how we have calculated it. Okay, so now we'll move ahead. Okay, so just a minute, I'll do. So we have also seen this formula before, right? So for calculating diffusivity, so this is the formula, and we have simply substituted all the values which we have shown in the previous page, on the previous page. So after putting down all these values, after putting in the calculator, we'll get diffusivity as 0.149 centimeter square per second. Okay, so we are done with also these questions, and now we'll move to another question as well. Okay, so we are moving with our last question. Okay, so last question states what? Let me write down the question first with black pen. Okay, okay. So this question states that I hope you all are able to see. Estimate CDAA. Okay, for CO2 in ordinary CO2 at what pressure 1.713 atm. Okay, and 373 Kelvin. It is known that DAA equals to 0.113 centimeter square per second at 1 atm and 298 Kelvin, at which condition C equals to P by RT comes out to be 4.12 into 10 to the power minus 5 mole per centimeter cube. Okay, so now we'll look at the solution. First, we'll understand what we have to estimate. So, in this, we have to estimate this CDAA, which is self diffusion only, and for these given conditions, we have to estimate. Okay, so now we'll look at the solution. Okay, so as we already know, this formula DAP equals to 0.00185883 T cube 1 upon MA plus 1 upon MB, okay, into 1 upon P sigma AB square DAB. Okay, this is the formula. So, but it is a matter of understanding what does diffusivity depends upon. So, what is changing here is temperature and pressure, right? So, we'll have to develop the proportionality. Okay, so DAB is directly proportional to, so we'll look here, temperature to the power 3 by 2, and what by pressure, inversely proportional. Okay, so this is the relation which we have to estimate so that we can calculate self diffusivity CDAA. Okay, so we'll do this. Okay, so DAA for second upon DAA and guess T second case to the power 3 by 2 P, similarly T1 3 by 2 P1. Okay, getting what I'm doing? So we have to calculate this. Okay, rest is already given. Okay, so DAA at second condition we have to calculate. Okay, so DAA1 we have already given is 0.113 centimeter square per second at 1 atm and 298. This is very first condition. And what is our second condition? Our second condition is 1.713 and 373 Kelvin. So this is our second condition. At this second condition we have to estimate diffusivity. Okay, CDAA. So this is what we have to calculate, and this is which we have been already given with. So we'll directly substitute 0.113. Okay, so T2. So what is T2? 373. Okay, to the power 3 by 2. P is already given, right? This is 1.713. Now T1. What is T1? This 298 to the power what? 3 by 2. Similarly, what is P? It is 180. So after like putting all these value in the calculator, what value we will get? So we'll simplify even further. Okay, to avoid. So this value comes out to be what? 0.823 centimeter square per second. So we have got this value, right? So yes, we are done with this question also. So we have completed all our questions which we have already seen in the PDF. So yes, thank you very much for the wonderful podcast with Shailendra Maurya and the questions which we have seen. Okay, I hope you get to learn more about the concept of estimation of diffusivity using various graphs various formulas and various techniques. And I also hope that you would have also understand the concept through which the relation we have developed for estimation of diffusivity. Thank you very much.